Hello, and thank you for attending our team's presentation for Code Platoon's DevOps and Cloud Engineering Capstone. The team members consist of Eric Basa Dennis, Jose Sandoval, and myself, Tanika Blair. Our team had a lot of fun working on deploying this application to the cloud, and we hope you enjoy this short presentation. InHome is a real estate management web application that's designed for landlords and tenants to efficiently manage rental properties, applications, and facilitate tenant and landlord communication. The application includes features for property management, lease agreements, and tenant requests, enhancing the rental experience for both tenants and landlords. The in-home application is deployed on AWS EKS, known as Elastic Kubernetes Service, for scalable and highly available infrastructure. Users access the application via a load balancer, which routes traffic to different application components. In our node instance and inside of our namespace, you'll see that we have two different pods. The first one serves the user interface. The second one handles the logic and API requests on the backend. And we also have an RDS for Postgres database so that we can have that served towards the backend. We also have CI and CD, continuous integration, and continuous deployment along with our EKS, as we are able to get new images pushed to Docker Hub, and then the EKS cluster will pull the updated images to seamlessly redeploy the application without any downtime.
Hi everyone, this is Eric and I will be talking about our AWS infrastructure that we built using Terraform. The Amazon resources we are using to build our infrastructure are AWS EC2, EKS, RDS, S3, DynamoDB, EventBridge, SNS, Lambda, CloudWatch, Route 53, and IAM. We are using different Terraform files to configure and build each and every resource for our project. These files include variables.tf, providers.tf, main.tf, nodes monitoring.tf, cluster monitoring.tf, and route 53.tf. I will begin by talking about our variables.tf. This file here is used to create and reference input variables for our Terraform configuration. Each variable listed within this file can be seen in our other files to be replaced by our default input string to help organize and enhance reusability. Our providers.tf file helps the configuration know which cloud service to point to, which in this case is Amazon Web Services. It also specifies which version, which region, and which profile to use from the AWS command line interface. The file that includes most of our resources to build for the infrastructure can be found within the main.tf file. Here we specify to build our Elastic Kubernetes Service cluster, our worker nodes that contain our application through the Elastic Cloud Compute Service, and our relational database service, among many others. Over to the right, we have our configuration within the main.tf file. We start the file by creating our S3 bucket to store our Terraform state file, which includes versioning and encryption. We also use it to store a file designed to create and store RDS snapshots for backups using AWS Lambda. The next included configuration are outputs for easy references to the important attributes of our resources, which can be seen on the right. We also have a DynamoDB resource that enables us to manage our state locking. This ensures we maintain consistency and integrity for the infrastructure state, preventing one team member to make concurrent changes while another teammate is changing something. Our RDS resource is responsible for creating and managing our PostgreSQL database instance on AWS for our application. Our next section contains our security groups. These security groups allow us to manage network access to our resources, specifically for our RDS instance and our EKS cluster, to include ports 22, 80, 443, and 5432. Our EKS section creates our EKS cluster and EKS cluster nodes, as well as a virtual private cloud, subnets, internet gateway, and route tables for the cluster. Nearing the end of the file, we have the configuration for Amazon Event Bridge and Amazon Lambda to schedule the creation of backups for our database every day at midnight, just in case it goes down. Finally, we have our IAM roles and policies to allow permissions for the resources to access and communicate with each other. Moving on from the main.tf file, we have another two files which are cluster monitoring.tf and nodes monitoring.tf. Cluster monitoring.tf creates a resource within AWS CloudWatch that enables the team to monitor the metrics of our EKS cluster to ensure that it is healthy. Some of the metrics we monitor for our cluster include how many clusters we have as well as how many nodes. Our nodes monitoring.tf creates a monitoring dashboard through AWS CloudWatch that enables the team to monitor the metrics of our cluster nodes, which includes CPU utilization that we have also linked and set up alerting through AWS SNS for whenever the allocated CPU in use goes above 50%. The last file we have is root53.tf, which configures domain name system settings for our application through AWS Route 53. It creates a hosted zone as well as the records for our subdomains and points to a load balancer. And now I will pass it on to Nika, who will talk about our Docker configuration.
We containerize both the front end and back end using Docker to ensure consistency across development and production environments. We built Docker images for the front end and the back end defined in the Docker file. Part of it you can see in front of you now. This part is for the front end. With the back end interacting with the Postgres database, all of this would be orchestrated together through a Docker Compose file. And that's used to bring up services locally so that we can simulate what would happen in production. We also have continuous integration and continuous deployment. And we have that as a pipeline using GitHub Actions. We automated our deployment process, and the pipeline kicks off when the code is pushed up to GitHub and pull requests are made to the main branch. The backend tests run in an isolated environment, and the front end uses Node so that the static files can be served by Nginx. Once these stages are passed completely, the Docker images are built and pushed up to Docker Hub.
Hello everyone, thank you for joining us today. My name is Jose and I will be guiding you through our Kubernetes implementation. Our Capstone project was all about deploying a full stack web application, which means we built a website with React frontend, a Django backend, and a PostgreSQL database. Think of it like a restaurant. The front end is the dining area where customers interact and consume. The back end is the kitchen where the food is prepared, and the database is the storage where the ingredients are kept. We started by deploying this app locally using Minikube, and then took it to the next level by moving to AWS's cloud environment using EKS and RDS. Today, I'll walk you through how we did it and some of the challenges we faced along the way. Local deployment with Minikube. Firstly, we used Minikube, which is like having a small-scale cloud setup running on our local computers. It allowed us to create a controlled environment for running our app. We split the app into 3 parts, one pod for the front end, one part for the back end, and one for the PostgreSQL database. Think of these pods like different kitchens in a food court, each preparing different types of cuisine, but sharing the same space. The front end kitchen serves the customers directly, while the back end kitchen prepares the orders. And the third kitchen, being the PostgreSQL pod, keeps track of all the orders, making sure nothing gets lost. Moving to the cloud with AWS EKS. Once we confirmed everything worked locally, we decided to take it to the cloud using AWS's EKS Elastic Kubernetes service. This is like moving our food court to a much larger shopping mall where we can reach more customers and have better facilities overall. Instead of having the third pod as our local kitchen for the database, we used RDS, which stands for Relational Database Service. It's like hiring a professional food storage service in the mall that handles all of our ingredients. By doing this, we let AWS handle the database management so we could focus on improving our front and back end. Deployment files. Our deployment files acted as the instructions for setting up each of these kitchens. They specified which ingredients and tools were needed and how many staff members should be working in each kitchen at any given time. For our app, these instructions control the lifecycle of the pods, how many copies or replicas should be running, and how updates were made. Services and networking. To make sure everything could communicate properly, we use services. If the front end needed to talk to the back end or the back end needed to access the database, these services provided the communication channels. It's like setting up the phone lines so different kitchens can coordinate orders efficiently. Some connections were internal, while others were allowed outside communication to customers. In this case, for the users to be able to access the website. Namespace, config maps, and secrets. We also used namespaces to keep things organized. Think of it as a sectioned off area for our kitchens in the mall where others can do the same with their projects under the same roof. Config maps and secrets were like recipe books for non-confidential and confidential information. For example, if an ingredient was a secret sauce, we kept that in a special safe place called secrets, while regular ingredients like salt and pepper were stored in config maps, just the common data. Challenges we faced. Of course, we faced some challenges. Setting up our deployment process wasn't always straightforward, especially because Django was a framework we hadn't deployed before, and neither was React. This full stack was actually something new for us, and it really tested our ability to put everything together that we learned throughout this cohort. The future. Looking ahead, we plan to get certified as AWS Solutions Architects, and we actually are in the talks about building more full stack solutions with infrastructure managed by cloud services as an actual team. We bonded and we actually worked well together. So this is an idea that we have possibly going forward into the upcoming year. The project was a great experience that really showed us the importance of automating deployments and really working as a team. So this really brought us together. Conclusion. To wrap things up, we took a simple web app and made it more resilient and scalable by moving it from a local setup to the cloud. Just like moving from a small food stall to a food court in a bustling mall, our app is now ready to serve more users with ease. Thank you for your time, and we look forward to your questions.